Okay. Hey, I'm just happy I didn't have to invite you to my summer solstice sweatshop. Baby steps. Good old Anne. The fact that it's protons, it's charges, I'm going to be thinking, what's our symbol for charge? What letter, what variable have we used for charge? It's measured in coulombs. What variable? Okay, I'm looking at equations with Q's in them. Yes? It's acted upon by a magnetic force of that while traveling perpendicular to a magnetic field. What speed are the protons traveling at? So I think I have a magnetic force and a charge that's equal to QVB. I think on your formula sheet, the Q is capitalized. I usually just write a lowercase q because I always think of it as a tiny charge. Habit. We would like to find the speed. So the speed is going to be the force divided by QB. What do I measure force in units? It's going to be the 5.8 times 10. Q. They didn't tell me. Or did they? It's a proton, yeah. Okay, and there's a reason a proton. I'm trying to get you to realize, unless I tell you the charge, it's going to be a proton and an electron. I think there was one question in the homework where I gave you an alpha particle that had 2 protons worth of charge, and that was because in Science 10 you look at alpha particles and radiation, but most of the time it's going to be a proton or an electron. 1.6 times 10 to the negative 19. B. What's B a symbol for, not force? What's B a symbol for? Magnetic field, those invisible tentacles that are going out. What's B measured in? Teslas. So it's going to be 0.6. The reason I'm emphasizing that there is going to be a question on your test where I say, find the magnetic field, and every year kids find the force. Or there's going to be a question on your test where I say, find the magnetic force, and kids isolate B and quit. No, there's more to it than that. Come here. 5.8 times 10 to the negative 14 divided by 1.6 times 10 to the negative 19 times 0.6. You get 6.04 times 10 to the 1, 2, 3, 4, 5? So 2 out of 2 if you got that. Otherwise, I would probably go half mark if I saw that, half mark if I saw that, half mark for the numbers, and a half mark for the answer. You're going to find often for questions where you're going to be using L, the length, in the diagram they will often give you 2 lengths to try and trick you. You'll notice here I gave you an 8.0 and a 4.2. First of all, let's look at the question. It says a wire is carrying a current of 5.2 amps. What's the variable for current? What variable, what letter do I use for current? So I'm already thinking it's going to be some of my equations with an I in them. If the force that the wire experiences is that, what's the strength of the magnetic field? Well, the force on a wire is Bil, B-I-L. They want me to get the strength of the magnetic field. That's get the B by itself. The force is 0.024, 2.4 times 10 to the negative 2, but that's less writing, divided by 5.2 times which length, the 8 or the 4.2? The section that's inside the field, because that's what's experiencing the force, not the 8. Oh, 4.2 what? I'm not doing that, actually. What am I really going to put here? 0.042. That's going to give me the magnetic field strength in Teslas. And I get a magnetic field strength of 0.1, I guess 0.11, 0.109. I would take a half mark off because doesn't stay a 9. 0.110 if I want to go to 3 sig figs. Teslas. 2 marks, again, half mark if, change colors, Mr. Duke. Half mark if I saw that, half mark for that, half mark for the numbers, half mark for the answer. If you use the 8 centimeters, 0.08, I'd give you 1.5 out of 2. And I'd also think bad thoughts about you. Yeah, I said it. Direction. Okay. This is a right-hand rule. This is the third right-hand rule because there's an external magnetic field. I point my thumb. Now, I'm going to do my screen here. My thumb in the direction of the current. I'm holding my fingers like I'm in a handshake. Fingers go into the page, down the page. This way, thumb, fingers into my screen, down the screen. I think the answer is going to be that. Yes? Before you turn the page, another good question would be to tell you the force is down the page and say which way is the current. Or to tell you the force is up the page and say which way is the current. Or to tell you the direction of the current and the direction of the force and say to you which way must the magnetic field be pointing. So all of those are fair right-hand rule shtick. In other words, I have no problem, Kiowa, giving you the force direction and saying work your way backwards to the other fingers. One of my students in my other class said, hey, Mr. Duke, thumb is current, fingers field, palm push. Oh, that's not bad. So whatever works for you. Okay? Now you can turn the page. An electron traveling that fast moves perpendicular to magnetic field of strength that. What's the magnitude of the force? You know what? This is straight plug and chug. The magnetic force acting on this is going to be QVB. It's going to be Q 1.6 times 10 to the negative 19. Mr. Duke, shouldn't you put a negative in? It said magnitude and force is a vector. The negative, forget it. V, 6.2 times 10 to the 6th. B, 8.5 times 10 to the negative 3. I get a force of you get 8.43 times 10 to negative 15? Yep. Vicus units for force. Yep. Okay. B. The electron is forced into a circle by the magnetic field. What's the radius? I could use my answer from A to solve B, but I'm going to do it as though they gave me B to begin with. That's a hint because that's probably what I'll do on the test as well. I am going to ask you to find a radius, or I'm going to give you a radius and ask you to find one of the other things in the equation. Did I say radius? What path is this electron tracing out? A circle. That must mean that magnetic force is what's pushing me in a circle. QVB is equal to mv squared over r. Yay, one of the v's cancels. The r is going to move to the top. The QB is going to move to the bottom. Stuff moves diagonally. In fact, you know, if we go full circle from the beginning of the year, I would look at Kevin and I would say, it was Kevin or it was Dale, it was one of you, and I'd say, hey, is this one fraction? And you would smile at us. So stuff will move diagonally, and we would do our little dance again, right? So we get this, R equals mv over qb. Now again, I would have no problem then, Jason, giving you the radius and the velocity and q and b and saying find the mass of the mystery particle. Or I would have no problem giving you the mass of the mystery particle, find the velocity at, or find q, get any one of those by itself. You okay with that? Just be careful in your cross multiplying. The key trigger though is, oh, it's being pushed in a circle. What path is it tracing out? What's pushing me in a circle? Mass. It's an electron, 9.11 times 10 to the negative 31. V, 6.2 times 10 to the 6th. Charge, it's an electron. B, magnetic field in Teslas, which was 8.5, you know what, 0.0085. 8.5 times 10 to negative 3. 9.11 times 10 to the negative 31 times 6.2 to the 6th divided by 1.6 times 10 to the negative 19 times 0.0085. You get 0.00415? I need to change these numbers because that's like a 4 millimeter radius, which is a little small. I probably need to make these numbers a little different, but okay, the math works at least if the physics sucks. 4.15 times 10 to the negative 3 meters. Okay. Be okay on that? Also have no problem asking you to do something. Hey, what's the kinetic energy? KE is a half mv squared. That hasn't changed. Oh, you know what? This is straight plug and chug. Mass, it's an electron. V, they gave me 6.2 times 10 to the 6th. Squared! Don't forget that. Is that right? 1.75 times 10 to the negative 17 joules? No, yes? I snuck that in because we're getting towards the end of the year. I thought I'd review a little work and energy. 1.75 times 1.75 times 10 to the negative 17 joules. 2 marks for that. Wow. Magnetic field strength. Now, what are we finding in question number 4, Raj? Magnetic field strength. Variable is what? Pause for 1 second. Got a latecomer coming in. Coming back to here. Spencer, what am I being asked to find in number 4?
The magnitude strength.
Magnetic field strength. I think he's in magnitude. Yep. So, and the reason I'm doing this, I'm about to give you a hint about your test. Solenoid is mu naught n I over L if they give me the length, which they did. If they don't give me the length, I use the little n times I, and they'll tell me the number of turns per meter. You know what would be a nice question would be to combine number 4, number 3, give you a solenoid, and before you can figure out the radius, you'd have to find the magnetic field yourself. Calculate it. Okay? That would be that, because to be honest, this is a little too plug and chuggish, even though you're doing some rewriting. B is a little too plug and chuggish. That might be a nice combination. I'll give you a solenoid, and you can find the magnetic field therein. It's going to be 4 pi times 10 to the negative 7. The permeability of free space. N, 600 turns. I, 4.5 amps. Or, you know what? Instead of telling you the current, I could tell you the voltage and the resistance, because if I give you V and R, haven't I told you I? Or I could give you how many watts and the voltage, because if power is V times I. In other words, I can certainly combine stuff from last unit and this unit. All over L, 0.032. I can type 4 pi times 10 to the negative 7. Some of you might have to go pi times 4 times 10 to the negative 7. You get 9.9 times 10 to the negative 3, 0.0099. I can't go 989 because that's going to get rounded up. So is that right? Am I wrong? Oh, thank you. That seems a little small.
Isn't that a candy from?
Yep. So how about 9.9 times 10 to the negative 2? Sorry?
Yeah, that's what I got too.
Okay, hang on. 4 pi times 10 to the negative 7. Oh, 4.2 instead of 4.5, Mr. Duick. Good gosh. Let's try that again. How about 1.06? Sorry, 1.06? 0.106 or 1.06 times 10 to the negative 1 Teslas. Is that better? Wow, did I botch that? Give yourself 2 marks for that, please. Okay. Can you give yourself a lovely score, please, out of, count 'em, 13.
Can you take a guess and guess all that?
Oh, and some cool videos and stuff as well. Questions? Lesson 1, you said, Josh? What number? Yeah. Number 2? Okay. There is a mistake in my answer key for 2, part 2.
I found that.
Left. Okay. And it's weird. I know what it is. Even now, every time I look at that picture, my brain, after staring at it for 2 seconds, flips it, and my brain is making that diagram come out of the page towards me, that current come over the top. And I know it doesn't, but somehow my brain doesn't see that. That arrow, for some reason, looks to me like it's coming out at me, even though it must be going away from me. So that was my dumb brain. Sorry, I was meant to mention that. So for lesson number 1, 2, part 2, left. Right? Current is curling this way, thumb points left. Next, any other questions from the homework? Yep. Lesson 2, number 2. This one here? Okay. I like this question. I'm not necessarily saying I like this question, nice review of everything. So here's the idea. It says that it is balanced, which means as an equation, I guess, gravity equals magnetic force. They used an Fm, I'll use an Fb for magnetic. They're in equilibrium. Gravity is going to be mg, because we're on the Earth. I don't need to go big G, big M, little m over r squared. Fb from a wire is going to be Bill. Oh, you good now? Okay. That's if I want to solve magnitude, I can get the B by itself. Oh, and the direction, well, the force is up. I'll point my palm up. Which way is the current going in the wire? To the right? Which way are my fingers pointing? That's why it's into the page. Yep. Okay. Any others? Okay. Also remember, I did give you the ultimate review, and for that, there is a full handwritten answer key showing all my steps online. Check that before you ask me.
Good way to cheat.
Okay. No good way to learn. So, we're going to continue on with magnets. This is lesson 1 of the next unit. This will be part of your final exam. Okay? On your final exam, there's 2 little magnetic units. We talk about your final. I think I've said this, but I'll repeat myself. Your final exam is going to be a booklet. The front page is going to be a cover page. Then when you open it up, you'll have 2 facing pages. This will be 2 questions from Unit 1. You're going to pick one, cross out the other one. Then if you turn the page, there'll be 2 questions from Unit 2, forces. Pick one, cross out the other one. Turn the page, there's going to be 2 questions from work, energy, and momentum. Pick one, cross out the other one. Turn the page, there's going to be 2 questions from circular motion, gravitation. Pick one, cross out the other one. 2 questions from electrostatics, 2 questions from circuitry, and then 2 questions from magnetism. One of the questions from magnetism is going to be on the unit that we just finished. One of the questions is going to be on the next 2 or 3 lessons. I'm not going to test you on the next 2 or 3 lessons. They're not going to be on a unit test, but they will be on your final. That way you can pick questions that you're comfortable with. Oh, and then the very last question, it's going to be one of 2 using principles of physics, right, to explain questions. Pick one. Okay? That'll be your final. What I want to explain to you is how we create, how we generate electricity. and I'm going to walk you through some of the discoveries that Michael Faraday and other scientists made that eventually led to that aha moment where they said, we can generate as much electricity as we need. Basically, it goes like this. Recall last day I showed you in the electric motor, I said, if we supply current, we can get motion. Maybe if we supply motion, we can get current. Maybe we can reverse that. So in the previous unit, we learned that when electric charges move, they produce a magnetic field. In addition, a magnetic field will exert a force on moving charges. Early in the 19th century, scientists such as Michael Faraday in England and Joseph Henry in the US were aware of these properties and both asked the follow-up question. If a current can produce magnetism, can magnetism produce? We're going to use notation to avoid having multiple V's in the same equation where one V means voltage and one V means speed or velocity. So we're going to use this EMF symbol, that curly E. This is going to be our symbol for voltage for this unit. It stands for electromotive force. It's badly named because it's not a force. It's not in newtons. It's in volts. It's an archaic, an old word that refers not to a force, but to the voltage of a cell, the maximum theoretical voltage before we hook it up to anything. So capital V and EMF in this unit will mean the same thing. If a piece of wire moves through a magnetic field, the charges in a wire will experience magnetic forces. Electrons are free to move, but we're going to pretend it's the protons that are moving. In fact, let's look at it. We're going to take this wire. Here's the wire. And we're going to move it. We're going to just grab it and pull it through a magnetic field. What's going to happen? Well, to figure that out, Kiowa, we're just going to target one charge. All of you right now, let's put a big positive dead center. Let's focus on that positive charge. That charge is part of the wire. Which way is the wire moving? Down the page. So which way is that charge moving? Down the page, in the wire. So all of you point your right thumbs down the page. The magnetic field is into the page. Which way will the positives get pushed in that wire? Sorry? What's going to happen is the positives are going to get pushed to the right. Oh, and also that means the negatives are going to get pushed to the left. What you've actually done is you have separated charge. That's exactly what a chemical battery does. A chemical battery separates positives and negatives, and then we force the charge through a circuit. Well, now we're doing the same thing. We're doing work in separating charges, but we're doing it not from chemistry, but through motion and an external magnetic field. So, since the charges have been separated, and separating charges takes work, we have voltage, because voltage is defined as work per charge. Energy per coulomb. We call this voltage induced by motion voltage, because the energy in this case comes not from chemistry, as in a Duracell, but from motion. We call this an induced voltage. Okay? You haven't created free energy, by the way. If you actually did this experiment, you would feel something tugging against you as you moved the rod. You would feel a force resisting you. That's the work that you're adding to the system, the force times distance, in order to separate those charges. In other words, motion can induce an EMF. Let's get an expression, but we're going to do this. Cross out the letter V, and let's replace it with our EMF symbol, because otherwise we're going to end up with lots of V's. We're going to start off with the definition of voltage. Voltage was defined as how much potential energy you had for every coulomb of charge. That's from your electrostatics unit. That's where the It was a change in voltage, but we're just going to go with the voltage at any location. Then I wrote definition of work. What is the definition of work? Work is what times what? Okay, so now we're going to write this as force times distance per charge. Which force? Magnetic force. That's what's moving the charges. So do me a favor, put a little B for magnetic force on the F. We have an equation for magnetic force on a charge. What's the equation for magnetic force on a charge that's moving? Manny, what's the equation for the magnetic force on a charge that's moving? Yeah, you were talking. Shush. Got your formula sheet in front of you? Good. Find me the equation for magnetic force on a moving charge. Yes, you're right over here, but I want Manny to find it. You guys see where we are? Okay. You just did a quiz on it. So we're in the magnetic unit. Find me the one that has F, force. That's on a wire. On a charge. What variable is charge? Mitchell, can you help him out, Mitchell? No? Raj, can you help him out? Trav. Yeah, Trav. Q, V, B. There, look up, look up, look up, look up, look up. There's the force times the distance, and then over Q, that came from our definition of voltage. Trav, what do you notice in this equation? Anything cancel? Anything cancel? Ah. Okay. Here is the equation. Guys, here is the equation if you want to figure out how much voltage you're inducing by moving a wire through a magnetic field. We're going to use our EMF symbol because I don't want to have two V's in this equation. And it's equal to the magnetic field strength. Instead of D for distance, I'm going to use L for length of wire. And how fast you move it. Oh, but once again, for our right-hand rule to work, the magnetic field, the length of wire, and the speed all have to be at right angles to each other. Otherwise, nothing's going to work. Is it BLV or BVL on your formula sheet? BLV. It is BLV? Okay. Sorry? The direction of the velocity. This way, there's your length, and then your magnetic field is into the page. They are all at right angles to each other. Well, speed. The speed's direction, okay, call it a velocity, but I'm ditching the vector notation because you're asking me a question I can't answer. The answer is, yes, these are all vectors. It's a vector cross product, which you don't know how to do. Use your right-hand rule. Okay? So here's our scalar equation. It gives us a scalar magnitude. V, which I'm going to use the EMF symbol for, voltage. And we have our external magnetic field, the length of wire, the speed of the wire, and you only get volts when they're all perpendicular. What if they're not perpendicular? This will answer your question better. So on the next page, here's a picture. Here, the length and the direction of the velocity are in the same direction. Let's use the same trick. Let's put a little positive right there. Which way is the positive moving? Well, which way is the wire moving? Down the page. So which way is that positive charge moving? Down the page. Which way is the magnetic field? So point your right thumbs down the page. Magnetic field into the page. Which way will that positive charge get pushed? To the right. Which way will negatives get pushed? Now here's the problem. If the wire is oriented that way and it's a thin wire, is there really anywhere for those positives to go to the right? Is there really anywhere for those negatives to go? You're not going to be able to separate the charges because there's no distance. I mean, okay, the wire has a tiny bit of thickness, but really, you're not accomplishing much at all. This is why they have to be perpendicular. So you can make a little note here. Although charges would, let me make this a little smaller, technically be separated, there is nowhere for them to go. Right? The positives would go there, and negatives would go there. They can't separate. They're stuck in the wire. Rotate that wire 90 degrees, and now you can really separate charges. You can put some distance between them. You can do some work, some force over a distance. You can store some energy, and since voltage is energy per coulomb, you've got voltage. Okay? So example 4 says, find the voltage induced by motion across the ends of this moving wire. So this is induced voltage, this is induced EMF. There's a B, magnetic field. There's a length, and there's a speed, a velocity, I guess, and our velocity is into the page. Are they all at right angles to each other? Yep. So if I want to calculate the voltage, it's going to be BLV. Manny, how big is the magnetic field in this question? Good, thank you. Manny, how big is the length in this question of wire? Don't say 80. 0.08? How about 0.8? Yes. And what's the speed? So if you had this setup, now this, by the way, is a terrible setup. You're just dragging something, but this is where Faraday started. How many volts could you create? How many volts could you generate doing this? Just about a 6-volt battery. 5.25? Yes? No? Yeah. 5.25. It's an EMF. It's volts. Which side of the wire will be positive? Because it says indicate the polarity, indicate what's positive and what's negative. Again, when I ask you a question like this, just focus on a single positive charge. Which way is the velocity of the wire? Read the question very carefully. Which way is the velocity of the wire? Into the page. That's what the X means. And since the charge is part of the wire, which way is the charge moving? Same answer. So all of you point your right thumbs into the page. Which way is the magnetic field, Jason? Jason, which way is the magnetic field? That's down the page. So thumbs into the page, fingers down the page. Which side of this wire will become positive, the left side or the right side? Hey. Okay. If we were to represent that with a battery, it would look, the positive would be on the left. Now again, this is not good because this means you got to keep dragging your wire through a really, really long magnetic field if you want to maintain a voltage. But we're going to start here and then get clever. Hopefully, Alex, if nothing else, I've convinced you motion inside a magnetic field with some cleverness can be used to induce a voltage. Now we just want to improve the system. But just with this, by the way, guys with me? There's some neat applications. Airplanes travel through a magnetic field. The magnetic field that they travel through is the Earth's magnetic field. Okay? You can think of an airplane, since it's made out of metal, basically as a moving wire. So it says, find the motion induced across the wings and indicate the polarity. Find the motion voltage induced across the wings and indicate the polarity. Well, voltage is going to be BLV. Clay, how big is the magnetic field of the Earth? It says in the question.
0.008.
Okay. By the way, if you're wondering about the direction of the magnetic field, if you're fairly high up, by this time the magnetic field is curving back down towards the Earth, so the magnetic field direction would be something like that. So there's the magnetic field. What's the speed? 320. Which length am I going to use, the 60 or the 150? I'm going to use the length that's perpendicular to the magnetic field and the speed, the velocity. Spence? Yep. How many volts will this generate? And by the way, they use this back in the old days when you could smoke on airplanes. My understanding is the little pop-in cigarette lighters that popped out after heating up ran off of this voltage. It's not free energy. Your voltage is energy per coulomb. Your gas mileage is lower by exactly that amount of joules per coulomb. So it's coming out of the fuel, but hey, may as well use it. It's there. May as well use it. 154 volts. I don't know if they still power stuff from that. I need to go do some Google searching and find out. What part of the plane would be positive? Well, let's put a positive right there, and let's track it. Which way is the airplane moving? So which way is the positive charge also moving? To the right. Magnetic field, once you're up high, is curving back down towards the Earth, so into the page if we're looking at it from the top. I think we'd end up with this part of the wing being positive and that part of the wing being negative. Yes? As I said, this lesson has lots of practice for right-hand rule stuff as well. So Faraday thought for a while. He said, yeah, I'm generating a voltage. There has to be a way that I can turn this into a battery. Well, a rudimentary start, the first thing is, if instead of sliding the wire through a magnetic field, what if we have the wire sitting on metal railings so that we're sliding it along the railings? That means the current can be conducted through in a loop. So if we connect the moving metal strip to conducting rails, well, then the strip will act like a battery and we'll get current flow. So you ready? Says, show that the polarity of the moving wire is like that of the cell. So we're going to argue that this left-hand diagram will behave like that kind of a battery. Let's see. Here is our charge. I know there's trillions of charges, but I always, Kyle, just focus on one dead center. Which way, Dustin, is the wire moving? Which way, therefore, is the charge inside the wire moving? Also to the? Read carefully, which way is the magnetic field? I printed it in the diagram. It says region field out of the page. So thumbs to the right. For me, my magnetic field is coming out of the page. Which way will that charge get pushed? Which way will that charge feel a force? Okay, now if I didn't have it connected to a conductor, we would get a voltage and that's it. We'd separate the charges and that's it. But because I've got it sitting on conducting rails, I'm going to get a current. I could even light this little light bulb or whatever resistor that is. Clay, question?
How many amps is that going to be?
Oh, not this setup, not terribly good. Trust me, we're going to get way better. In case you're wondering, we're going to build up to, instead of a single wire, spinning a coil of wires. That's how all generators work. But to get there, it's going to be some sequential processes to get there. But we haven't improved on that system. Maybe fission might improve on that. But for now, works pretty good. Hey, wait a minute. If there is a current flow moving, if there is a current flow, guys, if there is a current flow through the moving metal strip of wire, then there must also be a magnetic force, because once you have current, you have that. Right? Dustin, which way did you tell me the current was going to be flowing inside that wire? Which way did we figure out the current was flowing inside that wire? Down the page. Okay, so we started out looking at a charge, and because the wire was moving to the right, the charge is moving to the right, but it's also moving down. So let's go to this diagram. Let's put a little positive right there. I know it's moving to the right. Let's ignore that. Let's also realize it's moving down through the wire. Point your right thumbs down. Magnetic field is still out of the page. Down. I got to bend like this out of the page. Which way will the wire feel a force once the current starts to move? If you did this and you pulled that wire, you would feel a force resisting you. You would feel something tugging back against you. As you pulled that wire to the right, you would feel, wow, it feels strangely heavy. In fact, the faster you pulled, the more you'd feel it resisting you. Pause for a second.
Workout machine.
You guys with me so far? All right. I like example 8. Actually, no, I've told you I'm not going to test you on this section, although it might show up on your final exam. Oh, heck, I'm going to tell you this won't show up on your final exam. It's just cool, though. So here is Faraday's initial attempt to create a generator. A metal strip, we got a resistor, and we're going to pull this wire. It says the strip below is moving, is 12 centimeters long. Of course, I'm going to go 0.12 meters. I'll cross out the 12 centimeters. Nice try. It's moving at 4.7 meters per second. The external magnetic field is 0.08 teslas. And the resistance of the rail circuit is 0.025 ohms. Find, okay, A, the induced motion. Induced motion is that. Kohei, B is the magnetic field in teslas. How many teslas do we have here? Yep. L is the length of wire. How long is the wire? 0.12. Yep. V is how fast you're moving it. How fast are we moving it? Yes. How many volts are we creating? 0.08 times 0.12 times 4.7. Not much. You get 0.04152? This is not a very efficient way to create voltage, but it will create voltage. Is that right? 0.0, yeah. So I'm going to go 0.045 volts. Okay. Kyle, what does B want me to find? Current. What did I find in part A? Voltage. Is there an equation that has current and voltage in it? There is. Ohm's law from last unit. What was Ohm's law from last unit? V equals I times R. Could you get the I by itself for me, Kyle? Which V? The induced voltage. Which R? The resistance of this system. Did they give me the resistance in ohms in this question somewhere? Oh, what? So even though this system isn't generating a lot of voltage, if I divide this by 0.025, how many amps are we getting from here? Oh, this is better. Almost 2 amps. That'll get your attention. 1.8 amps. Kevin, what does C want me to find? On the wire? So it's going to be a magnetic force. Which one? QVB or BIL? QVB or Bill? Bill, how do you know? Current, I, and length of wire, not a Q. Okay. How big is the magnetic field? 0.08. What's the length of the wire? 0.12. Ah, sorry, I did length first. I should have done current. What's the current? We just figured it out with Kyle's help. I'll write 1.8, but I'm going to use my answer button. And the length of the wire is 0.12. How many newtons of force will we feel? 0.08 times answer button times 0.12. 0.0173 newtons. Yes. You noticed it there.
How much was that?
Oh, I don't know. Okay. But you know, Clay, that's a good question. Sure, let's do it this way. Clay, as you pulled it faster, what would happen to the speed? What would happen? What would happen to the current? So what happened to the force? The faster you pull, the more Mother Nature says, nuh-uh. The more Mother Nature says, I'm sorry, you're not getting free energy. It's the law of the universe. But if you're willing to pull faster, you can get bigger voltage. All right, Faraday's saying, look, I've got a rail sitting on conducting, sorry, I've got a wire sitting on conducting rails. He said, this looks just like a loop. Why don't I try it with just a straight metal loop? This was his next thought. Okay. If instead of moving a straight wire, we move a loop, do we still get induced voltage? Do we still get induced current? Let's find out. There's going to be let's look at a pause. First of all, let me zoom in. I'm going to argue, Dale, that this loop has 4 sections. I'm going to look at a positive charge, a little plus, in each section. Let's do the top one first. Which way is that positive charge moving? Which way is the loop moving? Which way is the loop moving? This is meant to be really easy. To the right, okay, so that positive charge is moving to the right. Magnetic field is out of the page. Which way will that positive charge feel a force? Now, here's the problem. Can it really go down in this little chunk of wire here? You know what? You're going to get almost no voltage from that chunk of wire. Also, I could have predicted that because that wire's length is parallel to the speed, and I told you they had to be perpendicular. In fact, we're not going to get any significant voltage from that chunk of wire either. But the ends are perpendicular to the voltage. Let's look at the front charge. Which way is this front charge moving? To the right. Magnetic field is out of the page. Which way will this front charge feel a force? Down, and that's going to give you a lovely current going that way. Hey, this will work. Or will it? Let's look at that back charge. That charge sitting right there. Which way is it moving? That way. Which way is the magnetic field? Out of the page. Which way will that charge feel a force? If you get 2 amps this way and you get 2 amps this way, what are you really getting? Nothing. Nothing. Okay? Opposing currents cancel out. No voltage. Rats. Wait a minute, Mr. Dewick. You said earlier that we actually, generators, have loops. We're going to have to get clever. Yes? Quick, money. How many more am I going to get done today? Ooh, a few more. Okay. Then he thought for a bit and he said, okay, if moving the wire will create a voltage, what if I supply a voltage? Will that move the wire? So here's the next setup. This is how you build a railgun. You may have heard the term railgun. Here's how you build a railgun. So in this circuit, the wire is at rest, but instead, we're supplying a voltage source right here. Okay? Let's follow the current. I guess the current would go like that. Yes? Make it bigger. And then it would go this way through the resistor. Which way will the current be moving in the wire? It's meant to be really obvious. Yeah, up. Okay? So, what's going to happen? Well, as soon as we turn on this battery, charges are going to be moving up the wire. So point your right thumbs up the page. Which way is the magnetic field according to this question? Out of the page. So up the page, out of the page. Which way will this wire feel a force? To the right. It's going to start to speed up. This is a railgun. Replace the wire with some kind of metal projectile that has wires going across. It's a railgun. It's going to speed up. Okay? Pardon me? Patience? Okay? So, for the circuit below, it says find the induced voltage. Well, your induced voltage is BLV. Right now, in this circuit, what's the velocity? Right when we start out. Look at the picture. In this circuit, what's the velocity right when we start out? 0. What's the direction of the current in the circuit? Well, this way, which is, you know what? I'm going to write it as counter clockwise. But the questions that we've just answered, what's the direction of the magnetic force on the strip? What did you guys say? Which way is the strip going to feel a force? To the? What happens to the strip? It's going to accelerate. To the right. With me so far? Now, I'm going to come back to Clay, because he answered this question earlier. Clay, as soon as the strip itself starts to move, not only do I have charges moving up the page because of the current from the battery, but because the wire is moving to the right, the charges are also moving to the right. So all of us, let's point our thumbs to the right now. Yes? Magnetic field out of the page? Yes? Which way will the charges feel the force? You know what? You're going to be forcing a current in from this battery. Mother Nature is going to be forcing an opposing current back at you. Back at you. Okay? So, what did you say, Clay, as the strip, what happens to the induced voltage? You said it increased, yes?
Yep.
What happens to the overall current? Well, we have current coming in, but as soon as it starts to move, we can look at picture number 11 here. We have an induced current, I'll call it IND, opposing the current coming in from the battery. So the net current decreases. You might have started out with 3 amps, but as soon as it starts to move, you have 3 amps coming this way, 0.5 amps going this way. Yes, 2.5 amps. What happens to the magnetic force? Well, if the magnetic force is Bill, what happens to the magnetic force if the net current goes down? With the rail gun, the thing starts off, taking off like a rocket, but actually, the faster it goes, the slower it accelerates. It'll still be accelerating, But initially, there's almost no opposing force. It's going to go off like a rocket. But the faster it goes, the faster the induced voltage, the smaller the net current, the smaller the force, and since F equals ma and the mass isn't changing, the smaller the acceleration. In fact, eventually, Spencer, you're going to reach a maximum speed when the current from your battery exactly is equaled by the induced voltage current. That's your maximum speed. Speed of the strip still increases, but the acceleration decreases. Okay? It says explain your answer using relevant principles of physics. I think we just have. Your first bit of homework. I'm going to get there next class. Number 1. Number 2. 3 is good. Seven is good. A little comic for you.
Yeah, so it's not durable.